So, in a one particle system, we don't know that when you have a particular space, let's just say this particular container, assuming, right? If you just like in a very small place and you have a particle in this particular location, we do consider various coordinates like the z, the y, and the z. And those coordinates actually describes the position of a particular particle. Now, let's look at what is happening in the subatomic state of this particular system. Now, to describe it, we introduce various interesting postulates, and those postulates involves various symbols that we are actually familiar with, like for example a wave function, and this wave function, which is expressed as this symbol, is actually crucial because this symbol is actually dependent on the coordinates of a particular particle over here, which are the x, y, z alongside time. Now, time is really crucial in terms of actually describing the moment in which the particle is, either it is here versus when it is in this particular region in space versus whether it's in this particular region in space. So, now let's look at how we express this particular wave function in terms of introducing probabilities. Now, when your wave function is actually squared, we get the probability that a particle is actually in a location at a moment in time versus another location at a moment in time. Now, this is actually expressed mathematically as follows. We have p into bracket x, y, z coordinates adding time to it. We cannot use semicolon in this case before time, and then this is equal to the wave function in the x, y, z, including time or absolute value squared. Then this is equal to splitting this wave function into two, where one part we kind of have aesthetics over there, which describes the particle in the x, y, z, and time, and multiplied by the other wave function, which is x, y, z, and time as well. Now, this particular formula that we have over here is actually describing a one particle system. Now, this one particle system then leads us to another explanation, which includes various observables which actually influences the property of that particle. So these observables all have their own operators from classical mechanics into quantum mechanics, and therefore to determine the quantum operators, we write the classical expressions from the observables in terms of the Cartesian coordinates and momentum. Now, looking at the Cartesian coordinates, we do know our x, we do know our y, we do know our z, and then by including the operator, we do get our observable, which is x. For our y operator, we do get our observable, which is our y, and for our z operator, we do have our observable, which is our z. Now, if you're going from position to momentum on the other side, our momentum on the x coordinate is expressed as the operator, where our I is multiplied by our Planck constants over 2 pi, which is expressed as h bar, with our eigenfunction in the x coordinates. The same thing is applied to our y, and the same thing is applied to our z. Let's just put it where h bar equals to h, or Planck's constant, over 2 pi. Now, don't forget that we do have our time as well. So our time case is actually expressed as the operator time, which is equal to the observable, which is our time. Now, how to replace observable px with operator is actually, in this particular case, or we can actually do it by transforming this into that. Either expressions are actually the same thing, and that is also applicable to our y, where you change this to our y and we change this for our z as we go from up to down over there. Now, what is a kinetic energy operator in one dimension? That is a topic for our next video, so watch out for that as we kind of break that down in terms of understanding what the kinetic energy operator in one dimension is when we are going from a particular classical mechanics expression to our quantum mechanical expressions, which is this particular expression over there. So thanks for following me through this. I truly appreciate it. See you on my next video. Be smart. Bye.